Okay, hi, we're going to talk today about energy changes. Okay, so you'll have experienced in reactions that sometimes I'll say, well, what does that feel like? You'll have your boiling tube or your test tube with some acid in, you'll put a piece of magnesium in, and I'll ask you just to gently test the outside and you'll feel that it's hot. Okay, that's an example of an energy change in a chemical reaction. So there are two different types of energy changes that we talk about. The first one is called an exothermic reaction. Okay, and that sounds like a mind-boggling new word to you, I'm sure, but we can break it down. So the thermic part comes from the word thermal, okay, which I'm sure you will remember from physics. If we talk about thermal energy, we are talking about heat. Okay, and exo here is like the word exit. Okay, and so what do you do with an exit? Well, you go out of somewhere, you leave somewhere. So that is go out. So an exothermic reaction, if we put that together, is one where heat goes out or is released. Okay, and that's what exothermic means. So let's have a quick look at an exothermic reaction. I'm going to draw you a beautiful picture of a lump of coal. Okay, and what I'm going to do to that lump of coal, obviously, is set fire to it. Okay, there we go. So that's now burning nicely. So whilst that's burning, if you stood next to it, you would feel the heat coming off that. So these little arrows just show that there's heat being released, and there's enough heat that you can actually feel it. Okay, and that's one of the big ways that you can tell whether something's an endo or exothermic reaction. And in fact, there's even enough heat energy that you can toast yourself a marshmallow over that piece of coal if you wanted to. So what's actually happening is that we've got a chemical reaction where we've got lots and lots of carbon. If we just draw that like that, I'm sure you'll recognize that these are carbon atoms, and we've got oxygen atoms as well. Okay, and these oxygen atoms, which go around in pairs, are in the air, and when they react, they will form carbon dioxide, okay, like that. Now, that carbon there is held together with bonds, and those bonds have got energy in them. These oxygen atoms are also held together with bonds, and those bonds contain energy. And this carbon dioxide is also held together with bonds. And what happens is that we've got bonds here that will break, and we've got bonds that need to be made. And we need to do an overall balance of how much energy is exchanged between those particles. We're going to get onto calculations with that a bit later on. But if you understand right now, we've got to break some bonds and we've got to make some bonds, then that is what I'm aiming for here. So in this case, okay, we've got carbon plus oxygen turning to carbon dioxide. Now, I'm not sure if you can actually see that, so I'll just move this down. There we go, right. Okay, so there we are. That's our chemical reaction. That's a solid, that's a gas, and this is obviously a gas. Okay, we can also have another look at a different reaction here. Okay, and just to start getting a little bit more in depth, this obviously is going to be a beautiful picture of a Bunsen burner. Okay, and I'm going to light my Bunsen burner. There it is. Okay, so we've got our Bunsen burner, and again, you can feel the heat coming off that, like that. Now, when it's on the orange flame, you don't feel that much heat energy coming off, but when you turn it to a blue flame, obviously you feel quite a lot of energy coming off. What's actually happening is initially here, we've got CH4, which is methane gas, and it's reacting with oxygen, O2, in the atmosphere, and it's turning into carbon dioxide gas and water vapour. Okay, because obviously it's quite hot. So when we open that hole at the bottom, there's more oxygen released into there, there's more reaction that happens here. So we get more heat energy given off. That's why the blue flame's hotter. So if now we look at the amount of energy released, okay, we write that, and the example here is that it's 890 kilojoules, which obviously remember joules are a unit of energy, per mole. And obviously a mole is just a quantity of particles. So for every 1 mole of methane that we burn, we get 890 kilojoules of energy released. Okay, so that is your exothermic reaction. I'm just going to pause the video and then we're going to talk about endothermic reactions. So, back again, endothermic, the word therm there again, thermic, sorry, is from the word thermal, so that means heat, but this time we've got endo. Now, I would like that, there's a couple of ways you can describe that. If you've heard of such things as an exoskeleton or an endoskeleton, an exoskeleton is obviously where you have a shell around the outside. It's on the outside, exo. An endoskeleton is what we've got. Our skeletons are inside our body. That means in. The other way to think about it is entrance. Has got the same first 2 letters, entrance, endo, and that is where you go in. Okay, so an endothermic reaction takes in energy. Okay, now endothermic reactions are far less common than exothermic reactions, but there's a couple of good examples. The first one is when you eat sherbet, dissolving, when the sherbet dissolves in your mouth, there's a reaction that takes in energy there. Okay, so that's an endothermic reaction. You might sometimes feel that it gets a bit cooler when you do that. Another example, which I'm going to draw out here, is if I've got a boiling tube, and in my boiling tube I've got a compound called calcium carbonate, CaCO3. And if I heat my calcium carbonate up, which is what this nice big red arrow suggests, what will happen is that the CaCO3 will release some gas, which you won't be able to see, but it's CO2. Okay, and so the overall reaction here is CaCO3, calcium carbonate. And if we want here, because that just looks like it just happens. You've just got some calcium carbonate and then it just breaks down. It doesn't, we need to heat it. Okay, so if we write heat with this terrible red pen above the top, hopefully you can read that, yeah. And it will turn to CaO, which is calcium oxide plus CO2. And that's a gas, that's a solid, and that's a solid. Any reaction like this, where we have to continually heat the reactant up in order for it to break down, is an endothermic reaction, because it's taking in energy. You're having to give it energy from your Bunsen burner or whatever your heat source in order for it to break down into the CO2 and the CaO. So this reaction is an endothermic reaction, and it's called thermal, which means heat, decomposition, which is breaking down. You might have heard of dead plants, for example, decomposing. Yeah, that decomposition means breaking down. So thermal decomposition means you're breaking it down using heat. Okay, and just as with the exothermic reaction, we looked at the amount of energy needed, but here we're going to obviously look at the energy taken in rather than the energy released. And this one here is 178 kilojoules per mole. Okay, what I'm gonna set you some work based on this, If you've got any questions, please let me know. I hope that's been fairly clear. Good luck.